Fundamental theorem of calculus tells us that differentiation and integration are inverse processes of each other. So if f of x is continuous on the closed interval ab, f of x is continuous on the closed interval ab, and uppercase f of x is antiderivative of f of x, then integral a to b f of x dx is equal to antiderivative evaluated at b minus antiderivative evaluated at a. In other words, the definite integral of derivative from a to b of any function is equal to antiderivative of the function at b minus antiderivative at a. We're going to use this to evaluate some definite integrals. Now, earlier we saw how we could use geometry to evaluate some definite integrals. We also use limit of Riemann sum to evaluate the definite integrals. Look at example number 4. So here we have 2 to 5, 1 over x dx. What is a function whose derivative is 1 over x? Well, that's natural log of x. And we're going to be evaluating the upper. So antiderivative is natural log of x for 1 over x, because derivative of natural log of x is 1 over x. So natural log of 5 minus natural log of 2, we can write it as natural log of 5 over 2. Let's see example number 5. We have 1 to 8 x to the power 1/3 dx. What is antiderivative of x to the power 1/3? Antiderivative of x to the power 1/3 is the function whose derivative is x to the power 1/3. That's going to be x to the power 1/3 plus 1 over 1/3 plus 1, and the bounds are going from 1 to 8. So x to the power 1/3 plus 1 is 4/3. Dividing with the 4/3 is same thing as multiplying with 3/4. And we are going to plug in the bounds from 1 to 8. The bounds are from 1 to 8. Okay, so 3/4 can be pulled out. 8 to the power 4/3 minus 1 to the power 4/3. 3/4 is going to be at the front. So 3/4, 8 to the power 4/3 is same thing as cube root of 8 to the 4th power, which is 2 to the 4th power, which is 16, and 1 to any power is just 1. So it turns out to be 15 times 3 over 4, which is 45 over 4. So this definite integral turns out to be 45 over 4. Okay, the next example, number 6, we are going to look at. Let's make some room for number 6. For number 6, we are going from negative pi over 2 to positive pi over 2 cosine of theta d theta. What is the antiderivative of cos theta? What is the function whose derivative is cosine theta? That is the sine theta. And we can go from negative pi over 2 to positive pi over 2. We could also use the property of definite integral here. Instead of going from negative pi over 2 to positive pi over 2, we could go ahead and say this is going to be 0 to pi over 2 cos theta d theta, because cosine is an even function. So both ways, it's going to be the same answer. So I will get sine pi over 2 minus sine negative pi over 2. We don't add a c. In this case, there's no arbitrary constant c added, because we will be adding a constant and subtracting the constant, and that will cancel each other. Sine of pi over 2, and sine is an odd function. Sine is an odd function, so negative can be pulled out. So this is going to be sine pi over 2 plus sine pi over 2, which is 1 plus 1. That's going to equal 2. We're going to look at example number 7. So for number 7, we are trying to think about the antiderivative of secant x tangent x. What is a function whose derivative is secant x tangent x? So going from 0 to pi over 4, I'm going to pull the negative out. Secant theta, tangent theta, d theta. Is there a function whose derivative is secant theta, tangent theta? Yes, that function is secant theta. So the antiderivative of secant theta, tangent theta is secant theta, and my bounds are going from 0 to pi over 4. So negative secant pi over 4, that would be negative secant pi over 4 minus, and when I distribute the negative from outside, it would be plus secant of 0. We can evaluate this and get the value of the definite integral. Next, we have number 8, which is going from 0 to 1, 4 over 1 plus t squared dt. Now, I can pull the 4 out, going from 0 to 1, 1 plus t squared dt. Now, is there a function whose derivative is 1 over 1 plus t squared? Yes, that is tangent inverse t. So 4 tangent inverse t, and I'm going from 0 to 1, which is going to be 4 tangent inverse 1 minus 4 tangent inverse 0. So tangent inverse 1 is pi over 4. Tangent inverse 1 is pi over 4. and tangent inverse 0 is 0. So it turns out to be pi is the area under this curve. So if we go ahead and graph this function 4 over 1 plus t squared, and we go from 0 to 1 and find the area under the curve, it's going to be pi. So we saw some examples of definite integral, and we used the fundamental theorem of calculus to calculate the definite integral. The Riemann sum limit was a very long method. Geometrical method does not always work, but this is always going to work. So fundamental theorem of calculus tells us differentiation and integration are inverse processes of each other, just like addition and subtraction are, just like multiplication and division are opposite to each other, or inverses to each other.